In an era of explosive growth in modern agriculture, machinery, artificial intelligence, and cutting-edge scientific innovations have completely transformed the way people plant, cultivate, and harvest crops. In the past, farmers relied entirely on manual labor and the unpredictability of the weather. But now, intelligent automated systems allow them to manage their fields with near-perfect precision. As a result, global food production has surpassed 2.8 billion tons per year, a figure that demonstrates the power of technology in securing the world's food supply. Beyond productivity, harvest times have been significantly shortened. Post-harvest losses, once a major concern for farmers, have now decreased by up to 40%, maximizing the value of every seed and every ton of produce. Crop quality is better preserved, staying fresh for longer, and meeting the stringent standards of today's market. From apples gently picked by robots, to onions automatically dried right in the field using thermal sensor systems, to bananas transported along conveyor belts and overhead cable lines, all of these form a vivid picture of an agricultural landscape entering an era of automation, intelligence, and sustainability. This is more than an improvement. It is a true revolution, opening the door to a future where humans and technology work together to create harvests more abundant than ever before. In Washington state, an area that accounts for nearly 70% of the United States apple production, farms have adopted highly automated harvesting lines. The machinery systems are specially designed for apple cultivation and operate based on precise technical standards. Large stationary shakers are positioned around the base of each tree. When activated, they generate preset vibration frequencies that target only fully ripened apples, minimizing the chance of dislodging fruit that has not yet reached proper maturity. Beneath the tree canopy, shields and soft cushioning pads are arranged in a shape tailored to catch each falling apple. The padding uses shock-absorbing materials to protect the fruit's surface, ensuring no bruising occurs that could affect storage quality. After collection, the apples are moved directly onto a conveyor system equipped with soft rubber fingers. As the conveyor carries them forward, the apples pass through an air pressure stream calibrated to remove soil, dry leaves, and lightweight debris without damaging the fruit's exterior. This continuous system enables high-volume processing in a short time. Before the apples are packed into storage crates, the entire harvest passes through an automated grading unit. Optical and weight sensors examine each piece of fruit based on size, color, and uniformity. Those that fail to meet the standards are diverted onto a separate line for further handling. The highlight of today's process is the AI-powered apple-picking robot. Equipped with high-resolution cameras, an image analysis system, and ripeness detection algorithms, the robot uses a highly precise mechanical arm that adjusts its gripping force for each apple. It operates continuously, day and night, maintaining a steady harvesting pace unaffected by weather or lighting conditions. The adoption of these robots has significantly reduced the U.S. apple industry's reliance on seasonal labor, which has become increasingly scarce and insufficient for large-scale production demands. Onions are among the crops that use a two-stage harvesting process with specialized equipment. When harvest time arrives, the onion lifter is brought into the field. The machine uses a cutting blade system to sever the roots, after which a lifting mechanism raises the bulbs from the soil with high precision. Immediately after being lifted, the onions are laid out in straight rows with even spacing, ensuring that the subsequent curing process occurs uniformly across the entire field. The onions are not collected right away. They must undergo a natural curing period of 8 to 15 days. During this stage, the bulbs rest directly on the cleaned field surface. Sunlight and wind gradually reduce the moisture in the outer layers. This process allows the skins to dry and harden, creating a stable protective layer that helps prevent microbial intrusion during storage and transport. Throughout curing, farmers use moisture meters and weather monitoring tools to ensure the onions are not affected by rain or high humidity. If unfavorable conditions arise, the onions can be lightly turned or moved to a temporary sheltered area to maintain quality. Once the curing period meets the required standard, the harvester performs the second stage of the process. This machine uses soft grippers or a lifting frame to gently raise each bulb onto the conveyor without causing scratches. On the conveyor, an airflow system combined with light brushing removes any remaining soil or debris. The onions are then transferred into large containers positioned at the rear of the machine. At the collection site, the onions go through an initial grading process. Bulbs that are uniform in size and free of cracked skins or mold are sent to the packing area. Those that do not meet the standards are routed to processing lines, where they are used to produce onion powder, dried onions, or other industrial products. This two-stage harvesting method helps preserve onion quality during long-term storage and long-distance transport, especially for batches intended for export. In many European countries, such as the Netherlands, Germany, and Poland, carrot harvesting is carried out using fully mechanized systems. As the harvester enters the field, the front guiding unit separates the rows and identifies the position of each carrot line. Depth sensors adjust the lifting blades according to soil type and root size. Two parallel soft grippers clamp the carrot tops right at ground level. The gripping force is controlled by pressure sensors to prevent breakage or cracking of the roots. Once secured, the machine lifts the carrots from the soil with a steady motion, avoiding strong vibrations during extraction. Right after being lifted, the carrots pass through a preliminary cleaning system. A combination of shaking and gentle brushing removes most of the remaining soil. Next, the leaf-cutting blades run continuously, trimming the tops precisely at the point where they connect to the root to ensure uniform sizing and facilitate later packing. The cut leaves are blown to one side for separate collection or for processing into livestock feed. After the tops are removed, the carrots move on to an outdoor conveyor belt positioned directly behind the machine. Here, the size sorting system begins its work. Mesh bars or graded filter slots with varying gaps separate the carrots into size categories. Large, medium, and small carrots are directed into their respective containers. Sorting directly in the field helps reduce processing load at the factory and saves transportation time. During operation, sensors continuously monitor conveyor speed, product weight, and the fill level of the rear containers. When a container reaches its limit, the machine signals a transport vehicle to approach for a quick swap, ensuring uninterrupted workflow. Thanks to this automation, the required labor force is significantly reduced. Harvesting speed increases dramatically compared to manual methods, while minimizing root damage during collection. The entire system operates continuously, enabling large areas to be harvested in a short time frame. Peanut harvesting is carried out through a two-stage process using specialized machinery. In the first stage, the peanut digger moves along each planting row. A cutting blade located below the soil surface severs the roots and loosens the entire pod cluster from the surrounding earth. A lifting and inverting mechanism then flips the peanut plants upside down so the pods are fully exposed on the surface. This arrangement ensures even drying while reducing contact with any remaining moisture in the soil. Once inverted, the peanut plants are left to dry naturally in the field for several days. Ambient temperature and humidity are continuously monitored with measuring devices to determine the optimal time for the next collection step. During this curing stage, the shells lose moisture, becoming firmer and more stable. This natural moisture reduction helps limit fungal growth during storage and transport. The second stage begins once the peanuts reach the required dryness level. The harvester moves through each row of cured plants. Soft grippers or pickup reels feed the entire plants into the processing chamber. Inside, a rotating drum begins to operate. Using continuous rotational motion combined with gentle impact, the drum separates the peanuts from the vines and roots. The rotation speed is precisely controlled to prevent cracking of the shells. After separation, a strong airflow removes dry leaves, small stems, and other lightweight debris. Only peanuts that meet the required weight and size criteria move on to the collection conveyor. Substandard peanuts fall into a separate compartment for later handling. Quality peanuts are transferred directly into a large onboard container positioned at the rear of the machine. The container is equipped with a fill level monitor, which signals transport vehicles to replace the container in time, ensuring uninterrupted workflow. Throughout the process, data on kernel moisture, impurity levels, and harvested volume is recorded to support additional drying or quality checks at the processing facility. This two-stage system helps maintain proper dryness levels, reduces the risk of mold, and ensures the standards required for processing or export. High-horsepower tractors used for deep tillage typically feature engines capable of hundreds of horsepower, allowing stable operation on heavy or highly cohesive soils. Attached to the rear of the tractor is a specialized deep plow designed to reach depths of 50 to 60 centimeters. During operation, the plow penetrates the soil, lifting and turning the lower layers to the surface while moving the topsoil downward. This process breaks up compacted soil layers that often form after multiple growing seasons or from repeated machinery traffic across the field. Breaking up these compacted layers increases the soil's air and water permeability. Newly formed pores allow air to penetrate deeper into the soil profile, creating favorable conditions for microbial activity. Plant root systems, especially those of cereal crops such as wheat, corn, and barley, can extend deeper, anchor more firmly, and absorb nutrients more efficiently. During tillage, the tractor is equipped with automatic draft control and depth adjustment systems. Sensors monitor soil hardness to maintain consistent depth, preventing the plow from rising or going too deep, which would increase fuel consumption. Many machines also use GPS guidance to ensure straight tillage lines and even spacing between passes, minimizing overlap and missed areas. Deep tillage also improves the soil's water-holding capacity. As soil layers are mixed, rainwater or irrigation can infiltrate more easily instead of flowing off the surface. This reduces erosion risks and creates a reserve of moisture for crops during dry periods. Regions with heavy soils, such as many areas in Europe and North America, commonly apply this technique before each planting season to prepare an optimal soil foundation for crop development. Deep tillage is typically performed when soil moisture reaches an appropriate level. If the soil is too dry, the plow cannot penetrate effectively, and equipment wear increases. If too wet, the soil structure may be excessively disrupted and prone to recompaction. For this reason, operators continuously monitor soil conditions to choose the right timing. Deep tillage is considered an essential preparatory step for large-scale cereal fields. When the soil layer is loosened and well aerated, crop yields can increase significantly, helping maintain stable agricultural production across Europe and North America. The center pivot irrigation system is a large-scale watering device widely used in modern agriculture. The system consists of a fixed central tower and multiple connected spans that form a pipeline stretching hundreds of meters. Each span is equipped with self-propelled wheels, allowing the entire system to move in a circular path around the fixed point at the center of the field. Water is pumped from a well or reservoir into the main pivot, then evenly distributed along the full length of the irrigation line. Each section of the pipe features multiple low-pressure sprinklers designed to reduce water loss and minimize evaporation. The spacing and flow rate of each sprinkler are calculated based on the crop type, planting density, and local climate conditions. Throughout operation, the movement speed of the system is adjusted to ensure uniform water distribution across the entire irrigated area. Newer versions of center pivot systems are equipped with soil moisture sensors. These sensors, installed at various points throughout the field, continuously send data to the central controller. When moisture levels drop below the preset threshold, the system automatically activates irrigation mode. Conversely, when moisture reaches the required level, the sprinklers reduce flow or shut off to prevent overwatering. In addition to moisture sensors, GPS is used to position and track system movement. Location data helps maintain the correct path, speed, and irrigation range, preventing overlap or missed areas. Remote control technology allows farmers to monitor and adjust settings via smartphone, including turning pumps on and off, adjusting travel speed, checking water flow, and monitoring the activity of each sprinkler. By integrating synchronized technology, water usage is reduced by up to 30% compared to traditional irrigation methods. Water conservation is especially critical in areas with low rainfall or arid soils. Center pivot systems help maintain stable soil moisture, contributing to increased yields and reducing dependence on natural conditions. The data collected throughout irrigation is also used for analysis, crop planning, and optimizing water application at different growth stages. Bananas are a major crop in many Asian and Latin American countries. A banana plant's growth cycle lasts from 11 to 14 months. In the early stage, the soil is deeply tilled to create an aerated environment that allows the roots to develop properly. Crop management includes staged fertilization, regular irrigation, and pest control. When the banana bunch begins to form, farmers cover the entire bunch with a specialized plastic bag to prevent insect damage, avoid scratches, and ensure even fruit development. When the fruit reaches standard size, the bunch, typically weighing between 30 and 50 kilograms, is harvested by 2 workers in a coordinated process. One cuts the stem, while the other supports the bunch to prevent impact. Immediately afterward, the bunch is hooked onto an overhead cable system running throughout the plantation. This system transports the bananas to the processing area at a steady pace, reducing transfer time and minimizing mechanical stress on the fruit. At the processing area, the bunch is separated into smaller hands. Workers wash them with clean water and use latex removal tanks to eliminate any remaining sap. Each hand is then graded based on weight, size, and uniformity. Export-quality bananas are packed into ventilated cartons to maintain airflow during long-distance transport. The cartons are stacked on pallets and placed in cold storage to control ripening prior to export or domestic distribution. In processing plants, bananas are also used to produce value-added products such as banana chips. The process begins with peeling and washing the fruit. Bananas are fed into slicing machines to create thin slices, about 3 to 4 millimeters thick, to ensure uniform frying. The slices are fried in hot oil at temperatures between 170 and 180 degrees. Once they reach the desired golden color and crispness, they are placed immediately into a centrifuge to remove excess oil. Next comes seasoning, depending on the final product: salt, sugar, honey, or cheese powder. After seasoning, the chips move into an automated packaging machine. Each plant can produce 12 to 18 tons of finished product per day, supplying both domestic markets and export demand. The banana pseudostem is not discarded after harvest. Instead, it is repurposed in the natural fiber industry. The process begins by peeling off the outer layers of the stem, then feeding the core into a pressing machine to extract the fibers. The crude fibers are soaked to remove impurities, then rinsed with clean water. After cleaning, the fibers are dried to the appropriate moisture level. The final step is brushing the fibers with specialized equipment to improve softness and uniformity. Banana fiber is lightweight, breathable, strong, and fully biodegradable. Today, it is used in high-end fashion, handicrafts, and eco-friendly materials, although production costs remain relatively high due to the labor-intensive processes and specialized equipment required. From mechanized fields to fully automated harvesting lines, modern agriculture is transforming at an unprecedented pace. The cultivation and harvesting processes of apples, onions, carrots, bananas, and peanuts all reveal the same picture. Technology is becoming a critical foundation for ensuring food security and improving production quality. These advancements not only help reduce costs, minimize risks, and optimize yields, but also pave the way for agriculture to grow more sustainably. Land, water, and energy resources are managed scientifically. Farmers gain new tools to improve their income, and consumers have better access to safe and reliable food supplies. This is the moment for every nation, every business, and every individual to continue driving innovation. Investing in technology, supporting modern production models, and prioritizing products with transparent origins will help maintain the momentum of global agricultural development. Let's move forward together on the journey to modernize agriculture. Let's support smart, environmentally friendly production solutions that deliver long-term value. Every right choice made today helps build a stronger, more resilient food system for the future.